Welcome everybody to this first lecture of this academic year, which we almost had to cancel because of the heavy rainfall last evening, and there was some flooding here in this building, so we were afraid we had to cancel this lecture, but luckily everything is okay. Welcome. It's wonderful to have you all here and to see such a full house. Thank you all for joining us. My name is Jaap Jansen and I'm program maker at Studium Generale. And Studium Generale is a department of the university that organizes extracurricular lectures, debates, lecture series, film and talk evenings, cultural events on all kind of different topics that might interest you, and they are almost for free, or most of them are for free, or almost for free. And what could be better than starting our season with a lecture about our social brain? Because a new academic year means, for a lot of us, meeting new people. And, well, one of the most important things in life is other people, is interacting with other people and understanding other people and trying to read other people. And, well, yeah, I hope that's what we're going to hear about more tonight. And the person who is going to guide us through this topic is Professor Frank van Overwalle. Thank you for coming to Maastricht. And he is a professor of social neuroscience at the Free University of Brussels, the Vrije Universiteit Brussel. And he focuses on the study of the social brain, especially the cerebellum, if I'm informed correctly, for which he leads several international research projects. And he has written a book, The Andere 50%, the other 50%. I don't know if he's going to say something about it tonight. What he is going to tonight is explaining to us how specific brain areas play a role in social thinking and in understanding other people. The lecture will take 1 hour, and after the lecture we have half an hour for questions and discussion, and we will end the session at approximately 9:30. Please give him a warm applause. The floor is yours, Professor van Overwalle.
Good evening. Do you hear me? Okay, yes, I hear me myself. Thank you for being here and for being interested in the social brain and listen for an hour to what I have to tell you. Besides listening, I will also do a few tasks and games with you so that you understand better what we actually do when we scan people to know what's happening in the brain. And most of the research I'm going to tell is indeed under the MRI scanner, so we can see which areas of the brain are activated when we do these social tasks. I've been here before, must have been about 10 years ago or so, and some 20 years ago my research on the social brain started, and in that period a lot of things have been discovered, things we didn't know, and even the last 5 years or so we discovered an important role also of the cerebellum, the little brain. So there's probably not much of an overlap between what I'm going to tell you tonight and what I told you, the other audience or similar people 10 years or so ago. So my talk is about the social brain, and this is already the start of my talk. This was a little quiz, and you probably looked at it, and you looked at the eyes of this person. That's the mind in the eyes tests. And who thinks this person is playful? You may raise your hand. Comforting, irritated, bored. The correct answer seems to be playful, but a lot of people had a different answer, and I must admit, me, myself, and my teammates always had difficulties with these tests. And it's an often used test, but it's not so valid test of the social brain. But it's a very classic one. Unfortunately, still used too often. But it's a good beginning to understand what I'm going to talk about. There are two major systems in the brain that are involved in social interaction. And the first one is the mirror system, or action observation system, for body reading. That's reading the body. And most importantly, what do we read with the body? We read emotional expressions like embarrassment, I'm late, I'm disturbing this crowd, and so on. People laughing, and so on. Schadenfreude a little bit. This is the most important part of body reading. Yawning is one as well, but also picking up objects. You can, by picking up objects, you can guess what this person is going to do quite often. And this system works because we kind of simulate, and that's why it's called the mirror system, what we see other people doing is what we simulate in our minds. And by doing this simulation, we kind of guess the goal of this behavior. So what happens is that this is a picture that I will show you quite often tonight, the brain, as you can see. The front is usually on the right, the back on the left, and this is a side view. It's not a cut in the middle. Once in a while, I'll also show you some cut slides. And this is a major part of the mirror system, where biological behavior, movement is detected, which is very important in social behavior. Imagine a rock is falling to you. Yeah, you just have to step aside and nothing will happen. You're saved. If a lion is running towards you, or your enemy is running towards you, stepping aside will not help, because this enemy or this lion will chase you, and you have to find other solutions. So it's very important to detect biological movement. Another system is involved in detecting where is this lion or this enemy running towards you. Is he running towards you, to somebody else, and so on. And from this, you can detect the goal of this person. And by using this system, for example, we can test this with these little tests that we give to babies of 3 months old. That's a study we didn't conduct, but this is something similar we did with adults. You have this one, right? Normal thing. Then this happens. The barrier, obstacle is removed, and then we get this. That's a bit strange, isn't it? We would expect this one. And the same is true for babies of 3 months old. They look like this. Longer, what is going on? And when they see a straight line, they are comforted and look normally again. So even at 3 months old, babies infer a goal behind movements. So repeating the movement without an obstacle doesn't make any sense, because the movement is goal directed to the right side, to the other triangle, or which represents some goal. And so even at 3 months old, babies have this notion of goal-directed behavior. Another one is this. What do you think this action represents? Somebody has make some guess? Yes? Yes, what could be another one? Yes? Two good answers. But usually okay, I'll start with this, but it's unclear what is actually going on. That's also a good point. So if I give you this context, that's before tea is served, what would you think? So we combine it here. What would you think? We think it's drinking, right? So this behavior here, and then we combine it with another context, after tea. What is you think this behavior is doing? Representing? Cleaning up, right. Exactly the same words. She's been here 10 years ago. So even the movement without any context doesn't tell us so much. With some context we can infer the goal. But even if, that's a little detail, even the movement itself, the upper movement is the one that is usually used for cleaning up. And the movement at the bottom is usually the movement used to drink. But anyway, context overrules this and tells us what the goal is. So that is what the mirror system is doing. And that's all I'm going to tell about this tonight, because I'm mainly interested in the more sophisticated, almost uniquely human capacity to read the mind, the mentalizing system. That's something that is a little bit present in apes, mainly, and I would say primates, and that's about it. A little bit in some birds as well, but it's not so well developed at such a high level as humans. That makes us unique. Of course, it doesn't work like this, as depicted here. How we actually read some other people's mind is not by some sixth sense either. It's by the brain that calculates something and gives us a possibility to infer people's mind. And I'm going to tell you about what exactly the brain is doing in order to give us the opportunity and make us capable of doing this. And actually, I have to tell you a long story to explain how this system works and how it developed. And we have to go back in evolution, back to the caveman, and before the caveman, primates, apes, and so on. What these animals discovered was that if they collaborated together, they could hunt for larger food, bigger animals. They could protect their villages, better protect them against enemies, larger, more important enemies, and so on. But it came at a cost. Namely, you have to collaborate. And collaboration is not easy. You have conflicts between what some consider the most important goal or the best means to reach the goal. You have to divide labor up so that you have people who are good at running and other people who are good at something else. So you need to develop some social capacities to work with the members of your group and to gain the benefits. This is not so simple, chasing a very large animal. And for this computations, you need a larger brain. So during evolution, your brain grew. And this is the social brain hypothesis. The hypothesis is actually the brain became bigger for Homo sapiens, and also before the predecessors, in order to deal with the social aspects of collaboration, division of labor, and so on. And this is an illustration of this. So the larger the group size, there's a lot of evidence showing that the larger the group size, the more members you have to work with, the larger the brain grew and became. Especially the frontal lobes expanded a lot. Now, what are these key areas that have developed and that I'm going to talk to you about? Well, the first one is take an axe, do like this, poof, and you hit one of the most important social brain areas, the medial prefrontal cortex. Now, you have a split brain, it's not very handy, so we need to glue it together. And so this area is also a kind of social brain area, just above your ears. That's the two main important. This is called the temporoparietal junction, or in an abbreviation, TPJ. I will often talk about the TPJ, the temporal parietal junction. So that's the area above your ears. The name is not so important, but just I will refer to it quite often. So these are important brain areas. Now, interestingly, these are also the brain areas because they came later in evolution, they also develop later. These are the areas that gets insulated in your development. It takes you until you're 25 years, more or less, before you are fully developed areas here. But before these areas are fully developed and insulated, or myelinaceous, difficult word, I will not pronounce it. So, and also there's more individual variation in these areas, because they're not tied to specific sensory information, but they kind of develop higher level concepts about the goals of other people and so on, and other high level concepts. So more cognitive concepts. And they're also called association areas, not directly tied to observation and sensory information. So these areas have a special status in some sense. And about 10 years ago, there was a great research project where they studied 1,000 participants and then looked at the major brain areas. I'm not going to tell how they did this in the brain. And as you can see, there are about 7 major brain networks. And one of these networks, the red one, is especially important, and it's called the default mode or mentalizing brain area. That is the area that is involved in thinking about oneself, thinking about other people, thinking about the future and the past of people, and so on. And here you see these 2 brain areas that I talked before, the medial prefrontal cortex on the right, the TPJ on the left, and there's also another one, the precuneus. I will not talk so much about this one. The precuneus is involved in setting the scene, let's say, but also for other purposes than social interaction. So I will talk a lot about this mentalizing network. Mentalizing comes from reading the mind, the mental state of other people and yourself, so mentalizing. What does it mean? Imagine a game where you play simply the same game, but you play it against a computer, against a functional robot, an android, human-like android, or against a real human partner. And you switch between any of these other partners, these 4 partners, and what happens is that the more human-like your partner is, the more these mentalizing brain areas become activated in the brain. This means that your brain, you are actively thinking about what is this person trying to do? What kind of strategy is this person using? What kind of counter-strategy against me is he deploying? And so on and so on. Which is totally absent for a computer. You know, this computer doesn't know anything about me, cannot infer anything. So it's probably random or programmed by somebody. It's a something. It's not thinking. Okay, what are the functions of this mentalizing system? I'm going to try to focus on 3 major functions that determine how you are able to infer the mind of other people. And the first highest level is that you store knowledge that you were able to infer from other people. So storing social knowledge, what kind of person is this? The second one is taking a social perspective. That is focusing on what this person is thinking about, believing, what that person sees, understands. So the mental perspective, the social perspective, and not necessarily your perspective. And then at the lowest level is storing social stories and especially sequences. So who is doing what and in which kind of order? That's low level. This goes back to the basics of action execution. So I begin with the first high level. What are we actually storing? What kind of things can we store? Then switching to social perspective, and then to the last part, social actions. Okay, let's start with social stories. Now you see this picture, and you wonder, is it really true that information comes in about people? Yeah, okay. And that we then really have the idea of these people, our knowledge about these people, kind of built in the brain, stored in the brain, like this picture depicts here. Yes, we do in some sense. And in order to show this, so here's the area. What kind of person is this? Who is this actually? This is. So that's the place we are going to, where this function is really taking place. Who is this person? How do you know? We did some research, but I'm going to do the medial prefrontal cortex. I'm going to do a test with you. And you have to tell me, I'm going to show you a number of slides, and you have to tell me what kind of trait is this about, right? So I show you this. What is this about? Anger? Aggressivity, yes. So somebody being aggressive, right? Good. What is this about? Yes, me. Younger age, I didn't put a picture of my latest. But what you see here, we repeat information about traits, we repeat information about people, and there are some brain areas that then kind of shut down. Because they say, okay, we know this already. That's exactly the areas that store this information. So by repeating something, somewhere in the brain, usually the brain gets very active, but some area gets down, less activation. There the information is encoded. That's why that brain area says, yes, I know already. That's what I do here. The knowledge is here. So by using this, we discovered two major brain areas. The one that has to do with the trait in yellow and the one with the person in red, and the overlapping area in orange. And as you can see, it's in the medial prefrontal cortex. It overlaps to a great extent, and it makes sense because a person is related to the traits. Think about your mother. Oh, how nice he was. Your father, well, he was a little bit quite demanding and not so friendly and nice as my mother, and so on and so on and so on. So important people are coded there and their traits. So this is really storing that information. The question is this used only for this? For social information? Is it also used for something else? That's a question that we try to resolve in another study. Because a trait is a kind of high-level abstraction of your typical behaviors, right? If you're often angry and irritated, people call you aggressive, right? So we had a social condition and a non-social condition, animals, objects, and we asked at a low visual level, describe this visually. So you would say, I see green, a guitar, a brown guitar, and so on and so on. She has brown hair and so on, black hair, and so on. The same with that object or animal. And then we would ask for the high level, generate personality traits that go together with this. So one is musical, another one could be romantic, playing a very romantic tune or something. Maybe you think about other ones. Concentrated, yes, all right. And then we ask something similar, generate categories. So you have to say, I wouldn't know what this animal is exactly. It's the wrong example because I should know. Some people might know, but the question here is, generate some category above this exemplar. Like an animal, very high level, that's a living thing, for example, something from this planet, and so on. These are high-level categories. Now we were looking, how would the brain react to this kind of information if we compare these high levels versus the low levels? What we saw is that, okay, the objects were most often green, persons were red again, indicated in red, and what you can see, there is some overlap in yellow, but most of the time the social medial prefrontal cortex is uniquely reserved for social information. There's a little bit of overlap. As if we use a little bit of these, let's say, high-level categorization processes also for objects. But most of the time it's social. Okay, let's now switch to the next thing, social perspective. How do we switch to the social perspective? I'm going to try to get rid of them. Okay. There we are looking at the TPJ, but before I go there, look at the fact that the center specialized for detecting biological motion actually is very close by. And this is a TPJ. We ask ourselves, which view do you take, the ones of the perspective that you take or somebody else? And how do we know that that area is involved? Well, sometimes this happens by some neurological accidents. This was an operation to get rid of tinnitus. I will try. Okay. And you know, this is a very irritating noise that you cannot avoid. So what they do, they build in an electrode surgically, and when that's done, after a few weeks, then they turn on the electrodes in order to mute the irritating noise, but not the other information. So you're not supposed to become deaf. So this needs a lot of fine-tuning, and in this person, they were fine-tuning this, and all of a sudden the person said, I'm getting out of my body. I see myself lying there. Oh my God. The surgeon immediately turned down the buttons, tried again at the same moment, the same amplitude. Again, the person felt like getting out of his body. And exactly the electrode indicated by the blue arrow. They have replicated this many times with other patients. And what it actually means is that if you activate this area, if you stimulate this area, something goes wrong with a kind of thing that the brain is doing, namely, it makes you think that you are in the middle of your body. It's a kind of illusion that works very well, right? Because if you have to grab something on your right side, this works well, left side too. Imagine now that you actually think your body is here, but you think that your body is there. There is some conflict between left and right for the object that you have to pick up here. Because if you actually think that you're there, you have to use your right hand, but actually you should use your left hand. So the best solution, since the beginning of animal kingdom, is to think you're in the middle of it. This is top, this is bottom, this is left, this is right. No problems, no conflicts. So the brain is constantly doing this. But if you trigger this area, the illusion is gone, and you have out-of-body experiences. What it means is that this is very important to identify yourself inside your body and to see the external world as outside yourself. So it then identifies you in comparison with the outside world, in comparison with outside people. People are not you. That's the beginning of it. You need to be able to do this, otherwise people are just you and vice versa. Something else. Look at this one. What is happening with this? Any idea what this means? Take a wild guess. Now everybody's silent. Nothing. Yes. Okay, you guessed it right. There was nothing going on. This is just a control condition. Look at this one. What happened here? Playing hide and seek, yes, for example. Following, chasing, and so on and so on. So we immediately see goals behind movements again, right? So the mentalizing system is also detecting this kind of things, of non-biological movement, so at a somewhat higher abstract level. But the most important task to be able to detect whether people can mentalize or not is the false belief task. Probably some people heard about it, but I will explain it anyway because it's so important, and that's something we will do tonight quite often together. So you have Sally. She has a red marble or toy, whatever, puts it in her basket, right? Then she leaves the room, and then naughty Anna thinks like, I want to have this, takes it from the basket in her box, and then when Sally returns, where will she look at to find her toy? Who says the box? Who says the basket? Wow, all mature mentalizers. Congratulations, usually you have a few ones that do the wrong thing. And did you realize it takes you up to 3-4 years old to be able to answer this question? So before 3 years old, many children cannot answer this question. Although under some circumstances with younger children, they are able to do this at the age of 1.5 years. But then you have to remove all conflicting information as it is. You should have to remove the box, for example, and then it works. So it's something we need to develop and learn over several years before we are able to do this. And it's very important to realize that people have their own mind. So people are outside you, but they have something similar as you They have their own mind, and you have to infer what is in their mind. And in order to resolve this, you have to know what these people went through and at what time they were absent and didn't know what passed after that. Right? And if you can reconstruct this sequence of events, you are able to infer what they know and what they are probably thinking about. There's a question.
Okay. What if the person who is experiencing the out-of-body sees this? Would she see Anne if her body was not there?
That's two different things. If somebody is experiencing out-of-body experiences, they never provide them with this kind of tasks. I've never heard, but yeah, who knows? But they usually do it on the, yeah. The only, these are, let's say, these out-of-body experiences are accidents. They are not supposed to be ethically allowed to be replicated because you're doing damage at that point. So nobody will study this or be allowed to do this. So this is an important task, and we will do this together. So in order to know what your answers are, if it's the answer is left, lift your left arm, which is my, left arm. Yeah, lift it. Try it now, yes. And if it's right, you make some noise, ramble, right? You can do this on your own body, somebody else's body. Here, you're allowed to use whatever is available, right? Okay, this is the task. You see here one of the most famous Belgian heroes, the Smurfs. Small, but important, for us at least. And they are looking at the screen, and this happens, right? And then when the question mark appears, you have to tell where does he think that the ball is located, left or right? Nobody raising a left hand. Oh, I didn't check these two. Okay, so this is again a very brilliant class. Nobody got it wrong, right? Right. That's to help me out. Go on. Watch out. Some people have difficulty. Some raising the left hand, but it's right. You have to take into account what that person has seen last, right? What he knows. It's the he, it's Papa Smurf, right? Another one, watch out. Okay, you got it right. That's good. Left. Aha! Now we have Smurfette. And the question mark will appear next to one of these two Smurfs and give the answer for that Smurf. All right? So now it's on the left. See what happens. With some hesitation, but yes, correct. Yeah, you get it all right. Good class here. You corrected it. Okay, yes. Okay, wow. I'm surprised to see a class that is doing so well. Usually, you have some substantial minorities doing it not so well. I wouldn't say wrong, but... Okay, what we found in a study using these kinds of little animations is that when the two Smurfs were looking at the screen and could see what was happening throughout the whole event, that the TPJ was not very active. If one had a false belief, it raised a little bit, but especially if the two had a false belief, the TPJ was most activated. Although one might think that if the two have the same story, you have the same story to infer, that's easier. Actually, the TPJ has to make a distinction for two participants. We continued this research with 3 and it doesn't change anything more. So 2 is the maximum apparently that the TPJ is raising. If it's 2 or 3 or more, then it's just the same. So in taking into account the beliefs of other people, the TPJ is very important. And there have been other studies doing this. Another study where we also looked for what is the origin of this function, because it's a function that came in late during evolution. And so what the brain is typically doing is capturing a function, using a function that existed before, but then applying it for other means. And one of these functions is orienting yourself in something important, salient in the external environment. So if you hear a noise, you look at the place. If you see bright light, you will turn your attention to that place where this particular event happens. And that's what we call spatial reorientation, here indicated in yellow. So it's more or less at the same position as the TPJ. But then we have a belief task. The spatial belief task, as you can see here, is spatial, is left or right. It's not verbal, but it's spatially. You also have to say left or right. And the original spatial task is also left or right. And as you can see, there is a large overlap in rows, but that's the original orientation, yellow. But here the belief orientation, let's say, is much larger, using a much more expanded brain area, but still connected with the original brain area that was originally there before Homo sapiens involved in detecting the beliefs of other people. We have to reorient our thoughts not to the external world, but into the world of the other person and try to infer from inside that person's brain, mind, what is going on. So, as you can see, that's what really often happens. The brain will expand and use all the processes that have been used before in order to develop newer processes. The third function is storing social stories, and in order to tell stories, sequences are important. You have to start with A, and then B, and C, and so on in the story. So that's the order by which you infer the actions of another person. That's the cerebellum. That's the posterior part of it. And in the anterior part of it is already an older brain area that was taking care of the order of your own actions. Why is this important? Because that's how you learn to walk, to speak, to talk. Because these are repeated sequences that you can automatize. That's how you learn to ride a bike. By doing it over and over and over again, the cerebellum says, oh no, I know this sequence, I know what to do, and now you have to do this, and you do it finally automatically without any thinking about it. Walking, at the beginning babies cannot walk, but they learn to do this, and so on and so on. So it's crucially in your development. Now the claim is that also for understanding actions outside you of others, you need this brain area. And we have this has been a discovery since 2015. Nobody knew that the social inferences and social brain was involved in the cerebellum. But there is massive communication from the larger brain, the cerebrum, to the cerebellum, the small brain, the little brain, and back. So all information in the larger cortex, upper part of your large brain, presents information to the smaller part, where some modules are ready to say, yes, this is a sequence that I recognize, go on, continue what you are doing, or something is wrong in the sequence. A warning goes to the larger brain in order to prepare you to adjust your behaviors. Like, for example, you're riding a bike, all of a sudden there's a large wind, a strong wind, and you have to adjust a little bit your movements in order not to drop and fall. Okay. The larger brain has 16 billion neurons. How many neurons do you think has this little brain? I'll start with an easy question. Less, about equally, same number, or more? Who thinks less? Who thinks more or less the same? Who thinks more? You can read my mind. I wouldn't ask the question when it was too obvious. Okay, so amazingly, there are more neurons there in the smaller part of the brain. But they are somewhat more simple. They're not so sophisticated. But how many? Take a wild guess. 2 times as much? 3 times? 4 times? Raise your hand if you agree. 5 times? 6 times? Okay, 10 times, or between 5 and 10? More than 10. Okay, I see nobody dares to guess. All right, I'll tell you, 4 times as much. And you will never forget the number because it's a very sexy number. So if there's anything you remember from this talk, it might be this. Right. So many neurons are involved in this. And a large part of it is also involved in social mentalizing. And we wanted to discover this. So this is the motor sequences from your own body in the anterior cerebellum. And this is social sequences which go wrong here for the posterior cerebellum. Why the posterior cerebellum? Imagine the brain is evolving during evolution. The frontal parts are growing. The cerebellum also needs to grow in order to respond to these sequences, but there is the neck standing in between, so it grows backwards. So simple. There's area available here, so this grows, and here it's only at the back. But it's doing more or less the same thing. So we discovered that the cerebellum was doing something in social mentalizing. But what exactly? So here you have these 7 networks, and we see that in the cerebellum you see these same networks recurring in a primary, secondary, and even a third representation. And we are, of course, interested in mentalizing in the red area, the red socialist area, social area. What's a good, the person who used this color scheme probably had some feel for social because he colored it red. So we are interested in this part of the brain. So these are the 7 networks in slices. From top, the most anterior part, to the bottom, minus 84, is the most posterior part. We did a major meta-analysis of all social tasks we could find, fMRI tasks under the scanner. And then we did a meta-analysis and look at this for 2 kinds of tasks, event mentalizing, also false beliefs and other things are part of this, and abstract mentalizing. It's more about future, past, and abstract thinking about traits and so on. And as you can see, there is astonishing similarity between the network that was discovered earlier by other means and the meta-analysis that is related to social thinking only. The left one has actually been discovered by resting state, that is freely thinking under the scanner, no task at all. And the right one is only social thinking. So that was unexpected, so we explored this further. What is this doing? And the idea is that if the cerebellum is so important to learn motor sequences and automatize these sequences, perhaps it's doing this also for social reasons, the actions of other people. If you can expect what other people will do, it gives you a lot of advantages because you can react appropriately. And you not have to think at the moment, oh, what should I do? Because you know already more or less what is going to happen. So we developed some sequencing tasks. And I'll show you one to give you a feel of this. I put it in the right order, but participants were given this in a random order and had to put this in the correct chronological order. Now I give it to you already, easy for you, in the correct order. That's relatively easy. It's like a little movie, right? A truck hitting a stone, the stone hitting the tree, and the tree breaking, and so on. Another one, a social routine. That should be easy to recognize as well. That's what you usually do in a store when you buy something, right? No problems with this one. I'll give you a more difficult one. Well, please give me the order. Raise your hand if you know, don't tell it. I want to measure how long it took you to give the answer. I looked also at my watch and we're running already. 2, 1, 3, 4. So the guy sees that he still has one chocolate, then goes to the swing. Meanwhile, naughty Annie is there again, eats it, so he's very surprised. Now, what happens is that patients, if we do this with controls, healthy neurotypical controls, and compare to cerebellar patients, they do quite well for the mechanical, also for the social script, but they do really, really much worse for false beliefs. In order to demonstrate that the cerebellum is involved, we developed, in conjunction with false beliefs, also a true belief task, where there is no false belief because the guy, the boy invites Anna to eat together with him the chocolates. And then we looked at activation under the scanner, and as you can see, false belief and true belief both activated the posterior cerebellum. But this was one task. What happens in other typical social tasks? So we developed another number of tasks, kind of games, where we compared, and we also wanted to know to what extent is this socially, specifically social, and to what extent is it specifically tied, associated with sequencing. So we had a number of control conditions, like non-sequencing control condition. We also had non-social conditions. That was about objects who underwent something but were not people, and a combination of the two as well. So then, for example, we were interested in whether people were really, whether the cerebellum was really involved in trait inferences. For example, is this person a liar or honest? Right? So we provided information about this person, Lixia. She tells us testimony to the police, tells the truth, makes a confession, everything openly, and so on and so on. And you think this person is really honest. But the thing is, so you give 6 actions. In some of these conditions, you were required to memorize and reproduce the order of the events. That was a sequencing condition. And in the non-sequencing condition, you could give it in whatever order. Nobody was interested in the order. Right? That is a sequencing condition. Remember and reproduce the order. Okay, another was with, again, our famous Smurfs. You had 6 Smurfs. They went through a grid, followed a trajectory to reach some goals. So goal-directed behavior. And you had to infer what goal it was. So for example, and in some conditions you had to replicate the trajectory exactly, and in some conditions you did not have to do this. This is the non-sequencing condition. And again, we had the same thing, but then for balls or clouds and so on that were going through the air, but not social objects. So for example, here we have Papa Smurf walking around, a little bit of objects that he needs to avoid, and then, he goes for the cake, right? So initially you don't know what he wants to have, but now you know. Another task is implicit belief sequencing. So here is 2 Smurfs, Smurfette and Papa Smurf. Each of them see a flower. They are offered 1 or 2 flowers. But sometimes they turn their back to the screen, so they don't know how many flowers they get at the moment. That's a false belief, right? I'll give you an example, and you can do this together with me. So this is, the answer is 1. Okay, easy. This is 1. He still thinks it's 1. It simply turned its back. 2. 2. 1. And this goes on and on and on and on. But what happens is that, and what we never tell participants, there is an order that is repeated over about 16, 20 trials. That order is repeated. What we see is then that they become quicker and quicker, because implicitly, without you knowing this, you become quicker at this. You begin to expect the next trial. And when you take another order here, then it slows down again compared to the standard repeated order. And that's how we know they learned this order. And we can have several randomizations. The important one was the true-false randomization. But because when it's true, you have to look at the screen how many flowers they get. And when it's false, you have to remember how much did Smurfette get previous trial, right? So you can prepare yourself. And because you can prepare yourself, you become quicker. You automatize this sequence. Now, in all these studies, trait-implying actions, when we compare social non-sequencing or social versus non-social, the posterior cerebellum is involved. It becomes boring. Yeah, the grids thing, the goal-directed action, the posterior cerebellum again involved. Implicit learning of the Smurf and the trajectory and of the true and false sequences, again, the posterior cerebellum was involved. We also wondered, okay, can actually the cerebellum was actually meant to make it easier to predict the upcoming actions. Is this true? That's the hypothesis, the theory, but is this true? So imagine you have this kind of ride. Then the question is, would you expect this behavior? Probably not. Too peaceful. So what we did is, we started from a trait, Fumak is dishonest, and we asked participants from these 6 behaviors, select 4 that are not inconsistent with them, and in some of these conditions, rank order them in the correct chronological order, or just select them, that's all. So here is the rank order in the order in the correct chronological sequence. So we had some pilot testing, but that was the consensus about the correct order. Okay. And as you can expect, again, the posterior cerebellum was involved. So it's doing quite a lot, the posterior cerebellum, even to the point that we asked, but now imagine that you do something according to the sequence, but that your action is unexpected. Would the cerebellum also be involved in that kind of thing? So you do something in an order, that is, the sequence is there, you can replicate it, but socially something is wrong. For example, Lixia tells her testimony, truth, and so on, a confession, tells nothing to her mother. Tells her friend a lie. Come on, she's not the same person anymore. What happened here? Right? She must be lying. Or when she was truthful, maybe there was also a lie. So something is amiss here. And so we wondered, is the cerebellum involved also if that happens? And if we compare the 2 situations where something violation happened or not, then the posterior cerebellum is involved again. And there's a good reason for this. If something happens that is violating your expectations in another way, a social way, then you have to adjust your behaviors also. So the cerebellum better sends out a warning signal to the cerebrum, something is odd here, do something about this. Change your behavior, but do not follow the automatic pilot anymore, right? We've conducted about 20 studies like this on all kinds of goal-directed traits and preferences, intentions, beliefs, and so on. And here I try to summarize this in a short sort of meta-analysis. So we had one comparison where we looked for the social preference. Is the cerebellum more involved in social than non-social sequencing? And as you can see, large activation across many studies for social information. The second one, sequencing of social information, also activation. Social violations in green, also involved. Sequencing of non-social, actually there's also a little bit of activation in the posterior cerebellum, but it's the weakest of all. So indeed, it's not exclusive for social information, but the posterior cerebellum likes the social sequencing information the most. So, to summarize, at the front, we have at the highest level knowledge about a person, what this person is typically doing. At the mid-level, at the side of the brain, we can switch from our own perspective to the social perspective and back. And at the lowest level, in the back of our brain, we can infer and we can store information about the usual habitual sequence of events, which helps us to predict what's coming next. And now to end, what can this learn about dysfunctions of the brain? And I can still inform you about this. All right. You know, there's been a lot of research going on about autism, and autism is characterized by difficulties in social interaction, atypical behavior, and often also repeated movements and so on. And there's a lot of research showing that autism is caused to a large extent by genetic factors. So if you have an identical twin, an identical brother or sister who has autism, you have 50% chance of also having autism. But there's one factor that only emerged 10 years ago, that is, you guessed it? Take a guess. The medial prefrontal TPJ or the posterior cerebellum? Cerebellar injury at birth increases your chances to have autism also by 35%, more or less. So that's not so well known, and there are two studies that shows, so children that are born preterm, so after 6.5 months of gestation, when they have they've put these children under the scanner to see whether anything was wrong with them, also in the brain, and they found that if they had injuries, so let's say malformations in the cerebellum, then 2 years later, there was 37% chance that they would have autism. If they have something wrong with the cerebellum and the cerebrum was not important. The cerebellum is important, 31%. So if you take these two together, the cerebrum has little to say. It's especially lesions for the cerebellum. If you don't have lesions at the cerebellum, no chance to develop any autistic, whatever, symptoms. This was a study some time ago in 2007, but there's a more recent one who confirmed this finding. So again, after 7.5 months of gestation, those children who developed a large number of symptoms of autism showed distortions in the cerebellum as indicated here in the yellow parts. There are also studies showing that people with, now I'm talking about adults that were compared with neurotypical, healthy individuals, and adults had a lower volume of brain tissue in the cerebellum. At this area, this is the back view, and this is the posterior part, so the back part of it, also known as screws 1 and 2. But this is also important. If this is what the overlap across all these individuals is, then all these individuals have lower capacity for social processing in that part of the brain. But imagine now that their lesions or their difficulties or lower values extend to anterior parts, then they will also show some minor movement errors or problems. And this is also what happens. Some people with autism also show other difficulties in executive processing and so on. But the common denominator is social processing, and you can see it because the common, let's say, impairment is located at the posterior cerebellum, which is responsible for social thinking, and which during gestation will also determine the development of the cerebral areas, is one of the other research findings. So for example, if you show this task, it gets a present, and then thanks a lot, which of the two endings is the most appropriate one? The first one or the second one? Who chooses the first, well, the middle one, or the most rightmost one? Who chooses the middle one? The rightmost one. Again, a socially adept class. Wow. And look at this, when they get this task, neurotypical people have activation in the cerebellum, the medial prefrontal cortex. Autistic people have nothing. So they simply kind of make mistakes and they don't process this information quite well. We did a similar study with the picture sequencing test. You remember that one? Okay. Look at this. Neurotypical controls in blue do quite well, they do it very fast, much faster than autistic people. Autistic people are able to do this task, but they need more time to find the correct chronological order. So something is wrong in their sequencing. And they do quite well for the mechanical, the non-social condition, as you can see. What can we do with this? There are some things that we can do. We can provide specific training programs, or we can provide brain stimulation, as you can see on the photo. That's TMS, transcranial magnetic stimulation, in order to activate and stimulate the brain. One of the things we did quite recently was a training program based on the idea that already long known for long is that people with autism have somewhat difficulties in complicated mentalizing, not in easy mentalizing tasks, but in complex mentalizing tasks. But we also, with our research, found that they also have difficulties in sequencing stories. And that was true. So we invited people with autism, either in a waiting control condition or in a training program, and they had to retell stories. So they were given stories, and they had to retell the stories from the perspective of this individual, also taking into account the mentalizing content, their beliefs, desires, frustrations, and so on, but also the chronological order. And that's also something people with autism had difficulties with. Now you can understand why they sometimes misinterpret the situations, because they don't get the chronological order right. If things happen but in the opposite way, then all of a sudden the aggressor is not the first person but the second person if they switch the two people, right? So they were trained to pay attention to this, and as you can see, after training they did better on the picture sequencing task. They improved slightly but significantly. Also, their stories were more coherent. That means that their chronological order was more correct, the mentalizing interpretations were more correct, the contextual information was more correct. There's a whole coding scheme for this, very objective scheme. And as you can see, they did better on similar stories post-training in red, but also unused stories in green, so that they had never seen before. So they improved on their narrative capacities. So that's one thing we can do. And the doctoral student who finished this study is now going to help and treat people with autism, probably using this program in part to aid them to improve their everyday. This was conducted with adults, young adults who had autism. Another thing is brain stimulation of the cerebellum. You can use either transcranial direct current stimulation, that's a minor, mild current, or magnetic stimulation. And especially the first one is becoming more popular. It's very cheap and very easy to apply. So we started out with TMS, and as you can see, people after, these are neurotypical people, after stimulating them with TMS, transcranial magnetic stimulation, they became quicker in red. We did the same with the TDCS, so a mild current on the back of the brain, the cerebellum, and a return electrode on the cheek, or the chin is also used. They did better, but not in this study, not for the false beliefs, but they did better on all conditions. Also the mechanical condition, by the way, which is understandable because you stimulate the cerebellum and stimulation might go quite deep. So you might stimulate every part of the cerebellum. And similar things, but in order also for the belief task, they went quicker, but to make a long story short, it only was true for the cognitive task, control task, not for the social task. And we think this is a ceiling effect. Because we use neurotypical people, they were quite good at social inferencing, so that didn't go any faster. But for a new, unfamiliar cognitive task, they became faster. And the last one that I will show you is a task where we used stimulation, but also the scanner to see which areas were actually became more active after stimulation, using this prediction task. And as you can see here at the middle position, you see the posterior cerebellum. And on the right is a flat map of the cerebellum folded open, and there you see the mentalizing areas again. There's also an anterior, more anterior part of the posterior cerebellum. Yes, the naming is a bit complicated. Then the inferior part of the posterior cerebellum, that's how they call it, which is also more activated. And the ones of the bigger cerebrum are also the TPJ, the medial prefrontal cortex, and the precuneus were also more activated after stimulation than when we gave them a fake stimulation. So this, at least temporarily, helped them to better think about others. But again, when they performed the task, they did better on the cognitive task, control task, than the social task. And we think for the same reason, because these are neurotypical people, and we hope that with autistic people we will be able to show that this is also working for social inferences. But nevertheless, it were the social areas that became more active. And so I thank you for listening to me. I also, of course, thank all my collaborations and funding organizations for all the research that you have heard about tonight. Thank you.
Thank you so much for your interesting lecture and for all the tests you did with us and the beautiful visualizations. We have not so much time left, so we have till 9:30. If there are any questions, please raise your hand and I will come to you with the microphone. Is it you?
From the beginning of your lecture, what is the implication for people that are of different cultures, because they have a different mirror where they learn to train their social brain? So, I think it is very difficult for people from different culture to understand the social science they have.
The implications are first, with respect to the brain areas, these are probably the same ones. But of course, the tasks that you should give them should be adapted to their culture. At least in the European culture, we have developed different language versions of the picture sequencing task, and well, it seems to work well, so no problem there. But of course, also used in the United States and so on, but completely different cultures, that might, of course, need some adjustment, of course. Yeah.
Any more questions?
There's a question there.
Yeah.
Thanks. Regarding the social brain and also maybe the development, do you think that there are gender differences or sex differences?
Good question. I've never looked very carefully at gender differences. We recently did so for autism because it's well known that boys are more often diagnosed as being autistic than girls, but so far we haven't found any differences in these were performance measures, so not brain measures. But it's very hard. Usually, you know, a similar question is right or left hemisphere, right? Is there a difference? I can say after many studies, no. Sometimes it's on the right, sometimes it's on the left, sometimes it's at the two sides, but there's no way, it's not related to verbal information because there have been meta-analyses putting apart verbal information from pictorial information. Doesn't make a difference so much, so it's unclear.
Thank you. It's mainly based on visual information. Is there research what happens when you have oral information, music, speech?
Not in social research, as far as I know. A few ones with vocal information, yes, perhaps, but most of them is verbal or pictorial, that's true. Of course, in music, sequencing of especially music is an interesting area for research for the cerebellum and music and sequences in music, but I'm not an expert in this. But also there the cerebellum is involved. I would not know which area exactly, but it is probably the sensory motor area, I would guess.
Can fMRI be a diagnostic tool for autism?
Can it what?
A diagnostic tool
Yes.
for autism.
But as you know, it's so the structural deficiencies that have been shown that were especially for most people of autism are in the posterior cerebellum. You need a trained doctor who knows the cerebellum to see whether there are any deficiencies or not. So yes, they do this and they scan people in order to know whether, for this type of research and also for clinical purposes, it could be of value. Sometimes, for example, for young babies, the deficiencies are so obvious that even I can see it. Part of the cerebellum just disappearing. These are the most severe problems with the cerebellum. But there might be more smaller ones that are perhaps more difficult to detect.
Yeah, my question follows on from that because you talked about the training that you gave and you saw significant improvement afterwards, but do you expect there to be long-term improvement and to that to actually manifest itself in a physical change to the cerebellum so that you actually can measure that on MRI as well?
I expect improvement. How long it will last? We didn't have enough resources to test that because we could recontact these people, but that's not done yet. And I don't expect any improvements in structural or volumes. I expect that they use these strategies to overcome their limitations because it's genetically determined or by lesions at birth, problematic or impairments at birth. I don't think you can actually repair it. It's there, it will never go away. That's also what happens with autism. It's lifelong. But you can kind of cope with it more easily and interact in a more social way. And that's what we try to learn then.
I have two questions. The first is, did COVID isolation affect the social brain's memory function? Or is it actually possible to deliberately reset how your social brain thinks by isolating yourself from your normal social circles so that you can have a different perspective? And the second one is, can the age of the internet and deepfakes create a challenge for the human brain in its ability to separate true beliefs and false beliefs in social settings?
Okay, the first question. There have been studies of people being isolated for months in the South Pole. And sometimes it was extended because the winter was taking a longer time than expected. So for 9 months they were isolated, living together with the same 30 people. There was no difference in their social brain because, you know, if you have to deal with 30 people all of the time, and only these 30 people, there might be a lot of conflicts. I know from people coming from the South Pole and telling, oh my God, I had to help these people with some psychological support because things were going wrong. No, and there's also, they did some brain scanning and there was nothing wrong with the social brain. What did diminish, slightly, temporarily, was their spatial capacities, volume. And it's well known that the hippocampus is involved in this, and so it can increase for taxi drivers. Now they have their apps, so they don't need this, but previously they had to know all of London. So their hippocampus increased. So that was the place where there were decreases of volume temporarily, but not the social brain. Secondly, I didn't understand the beginning of your question.
Wait, I will give you the microphone.
I'm asking about the effect of technology and especially the internet, where we have artificial intelligence creating situations where people can create alternative realities that haven't existed. And so could that affect how the social brain interprets the actual reality?
That's a good question. I don't know how it will... That's a good topic of research. Because, yeah, If you create an avatar, it's the self, but another self, how you deal with this. And other people who are you can see in other avatars, and yeah. No clue yet. I think you will cope with it, your social brain will cope with it, but in somewhat perhaps unexpected ways.
Yes.
Hi. Are you aware of any cases where in a later stage of life there was trauma to the cerebellar part that was mostly discussed a couple of moments ago? So there was trauma to that part of the cerebellum, as in manner of speaking, which induced autism.
I'm not sure about autism, but what happens usually with trauma in the cerebellum, sudden trauma, is that, so for example, people have to undergo surgery to remove tumors in the cerebellum, is that they suddenly might become mute for several weeks and then become over-emotional, and so inappropriate social behavior and so on, yes. There's evidence of this. But interesting, they discovered a lot of affective, emotional, and cognitive disturbances, but at that time, nothing about the social. I don't know why, but it's only when we started to think about the social that all of a sudden people recognize, oh yeah, we've forgotten the social brain here. And actually, why we started the social is also an accident, because we had a colleague who was interested in the cerebellum, and we said, okay, we're working together on a project. Let's do something with the cerebellum and see how much social it really is involved with. So, yeah.
If
There's
there are
also
no-
a question here on
Yeah.
the front.
Just a question about mirror neurons. I know it's really controversial if they exist or not, and like, what is your view on it, and do they play a role in the social brain?
Yeah, I talked only a little about the mirror neurons. I think they do exist, of course. It's the thing we have in common with many animals. They have also very well developed mirror neurons, and primates, apes, and so on. And so by just seeing movements of others, they infer, for example, if you, actually it was discovered because in front of a, so they had electrodes implanted in an ape, macaque's brain, I think. And one of the researchers, it was very hot in Italy, and he bought an ice cream and was licking the ice cream in front of the ape, and all of a sudden the motor neurons of this ape were going on, indicating, I want to lick too. And so they discovered something is going on by just looking at other, yeah, in this kind, not members of the same species, but somebody else doing things, yes.
Okay. I would like to end this evening now, and there are no further questions. Thank you all for joining us and for being here. Thank you for the lecture. Tomorrow we have a lecture by a Dutch philosopher, Marjan Slop. On Monday we have a lecture about activism in the age of climate change, climate crisis. Tuesday we have a film talk about the Dmitriev affair, and Sunday we have an excursion to the Maastricht Museum. So please join us the next time, and I hope you enjoy this evening. Thank you.
And thank you for all your interesting questions and answering so well during all the quizzes.